Continuing with part 2 of section 10.2, we are going to focus on compound machines. In the previous section we talked about simple machines. Now we're going to talk about compound machines. What is a compound machine? A compound machine is really a machine that consists of two or more simple machines linked together, so that the resistance force or the resistance effort is connected to the resistance and effort of the second one. What you're going to really look at in a compound machine is you're going to put on an effort. That effort will create a resistance. That resistance of your first simple machine is going to be the effort of your second simple machine. So if we take a look at an example such as a bicycle, the effort is applied to your pedal. That is really going to be your first effort, E1. By putting on that pedal, you're going to get a resistance on the chain. That's going to be resistance 1. That resistance on the chain is also the force on the sprocket, or the force exerted by the chain, which is going to be E2, which is then going to move the wheel, which is going to be R2. What's important to note is that R1 and E2 are the same exact value. So R1 and E2 are the same exact value. They are linked by a simple machine. Now if you talk about distances instead of forces, instead of the force on the pedal in E1 here, we're going to talk about the distance on the pedal. Instead of the force on the chain, the distance of the chain. The distance of the sprocket, and maybe the radius of the wheel on the road. Those would be examples. Now our equations for mechanical advantage, MA, and ideal mechanical advantage don't really change. They say the same exact thing. Since we are combining two simple machines, we are going to just multiply our two mechanical advantages together. So the total mechanical advantage for a compound machine, MA, is equal to MA1 times MA2. And remember, mechanical advantage is equal to FR divided by FE, so really you're going to have FR1 over FE1 times FR2 over FE2. Now remember, from up here, R1 and E2 are the same value. Well, if FR1 and FE2 are the same value, they cancel out, and really you're going to take F2 divided by F of R2 divided by F of E1 to really figure out your total mechanical advantage for a compound machine. So you're going to multiply those two values together. Moving on to when we talk about mechanical advantage. Mechanical advantage is going to be the same way. Ideal mechanical advantage is equal to dE divided by dR. Well, that's really equal to, we're going to take IMA1 times IMA2. Now remember, the equation for IMA is dE over dR. So if we take that, the distance of effort is our pedal. The distance of resistance is the front sprocket radius. The distance of effort 2 is the rear sprocket. And the distance of resistance 2 is the wheel radius. So that's an example of a compound machine. Now the examples of compound machines in which we use are simply going to be oriented around a bicycle, because a bicycle is a great example of a compound machine. So you're going to take the two examples that we have, or the two equations that we learned. The MA is equal to MA1 times MA2, and the IMA1 is equal to IMA2, and you're going to apply them to a problem. Now instead of going over a problem on the smartboard, we're just going to do the physics example problem right here that I have from my Word program. So bike problem. A bicycle has a gear radius of 4.5 centimeters, a wheel radius of 38 centimeters. The pedal arm length is 9.0 centimeters. When a force of 150 newtons is exerted on the pedal, the chain moves 10 centimeters. The efficiency of the pedal and chain is 90%, and the chain and wheel is 93%. We have a whole lot of measurements to figure out here. A whole lot. Well, let's do first things first. You could write these on the top of your sheet if you wanted to. I'm going to put them underneath A, and then I'm going to erase them. So make sure you have them somewhere on your worksheet. What we're looking at is we have two systems. We have pedal chain, which is 1. And then we have chain wheel, or gear wheel, which is 2. Now, what we're going to have here is we have a bunch of things for this. We have distance of effort, we have distance of resistance, we have efficiency, we have force of effort, and we have force of resistance. Now, we have the same exact for the second one. We have distance of effort, distance of resistance, efficiency, the force of effort, and the force of resistance. And we have to kind of go through and decipher what we have. So a bicycle has a gear radius of 4.5 centimeters. Is that going to be in our pedal and chain, or is that going to be with our chain and wheel? Now remember, we said it's kind of the gear / chain. So is that our effort, or is that our resistance? Well, the wheel is our resistance, and it doesn't say anything about it says the wheel radius is 38 centimeters. So we have two distances applied. First off, a gear radius of 4.5 centimeters. It's the distance of effort, and our distance of resistance is 38.0 centimeters. Next up, the pedal arm length is 9 centimeters. Well, what is starting this? Is that distance or resistance? Or sorry, is that effort or resistance? We're pushing on the pedal. So our initial DE1 on the pedal is going to be, our distance is 9.0 centimeters. When a force of 150 newtons is exerted on the pedal, when a force of 150 newtons is exerted on the pedal, is that effort or resistance? You are dealing with the pedal, so that is effort. So our force of effort 1 is 150 newtons. The chain moves 10 centimeters. Well, that's our only remaining distance that we don't have is DR1, and that is the chain. So we're going to go in and put in 10.0 centimeters. The efficiency of the pedal and chain is 90%, so we're going to go 0.000. And the efficiency of our chain and wheel is 93%, so we're going to 0.930. Now there are 3 pieces of information we don't have, and we are going to have to solve for them. We do not have force of resistance 1, we do not have force of effort 2, and we do not have force of resistance 2. But all of those pieces of information we will be able to solve for. Also remember that if we solve for force of resistance 1, that automatically is our force of effort 2. So really, there's only 2 things we don't know, are both of our forces of resistance. So let's go ahead and let's see what we can do to solve the first problem A. As I cannot apparently circle here. Holy Moses. So in A, as I'm finishing erasing, in A, what is the resistance force on the chain? Are we trying to solve for our first resistance force or our second resistance force? We're talking about on the chain. Well, remember, in our first example, in our second part, the resistance is the wheel. So in our first part, the resistance is the chain, so we're trying to solve for FR1. Well, go back to what we learned about our equations. Efficiency is equal to work output divided by work input, which is equal to FR times DR over FE times DE. Go ahead and plug in numbers. We know the efficiency is 0.90, which is equal to FR times 10.0 divided by 150 times 9.0. When you go ahead and solve for that, what you get is FR1 really is 120 newtons. What else does it tell us? That would tell us that FE2, or the force of effort in our chain wheel combo, is also 120 newtons. So we move onward, and we want to solve for what is the resistance force exerted by the wheel. We are almost there. We're going to do the same exact thing. What is the resistance force exerted by the wheel? Now we are solving for F of R2. Well, we have F of E, we have FE2, DE2, and DR2. So we can go ahead and solve. Efficiency, again, is equal to FR times DR over FE times DE, but this time we're going to use the gear wheel numbers, so our efficiency is 0.930, which is equal to FR times 38.0 divided by 120 times 4.5. When you go ahead and solve for this, you figure out the force of resistance, or the force of the wheel on the road, is 13 newtons. C, what is the MA of the entire system? Well, the equation for MA is equal to MA1 times MA2. Now remember, MA is FR over FE. So we go ahead, FR over FE times FR2 over FE2. We go ahead and we're going to plug things in. Our FR1s is 120 over our FE1, which is 150, times our FR2, which is 13, divided by our FE2, which is 120. Our 120s cancel out, and we're really left with 13 divided by 150, and our MA is 0.087. Continue now with part D. D is asking what is the IMA of the entire system. Well, we're going to do the same thing we did with MA, except IMA is equal to IMA1 times IMA2. Well, IMA, remember, is equal to DE over DR1 times DE2 over DR2. We're going to go ahead and plug in numbers. Our DE1 was 9.0 centimeters. Our DR1 was 10.0 centimeters times our DE2, which is 4.5, divided by our DR2, which is 38.0. Multiply and divide, and our IMA ends up being 0.110, or 0.11 since we're stuck with two sig figs. So we figured out our FR and our FE that we didn't have. We figured out our MA, we figured out our IMA, our ideal mechanical advantage. Our last step for efficiency is what is the efficiency of the entire system? Well, remember, efficiency is equal to MA over IMA. We already figured out MA in question C, part C. MA was 0.087. IMA was 0.11. 0.087 divided by 0.11 gives us 0.790, or 79.0%. Now, it seems like a very lengthy process, and it kind of is, but the most important piece of information that you can get, and the very most important piece of information, is in regards to you need to know what your DE and DR is. So remember, your initial effort is on the pedal. The resistance is on the chain. Your force of resistance 1 is equal to your distance of, your force of resistance 1 is equal to your force of effort 2. which is the force on the gear or the force on the chain. And then lastly, your wheel is your resistance to, whether it's distance or force. On the back side of your simple machines sheet, which you already got in class today, you'll have the opportunity to do one of these bike problems. If you have questions, you'll be able to talk about them in class. Have a great night. We'll see you tomorrow.